The cosmos is all that is, or ever was, or ever will be. Carl Sagan's words capture a truth we have all felt, standing beneath a canopy of stars. That profound sense of wonder, the feeling of being both insignificant and deeply connected to something infinite, is what we are exploring today. This journey into the tales of the infinite will reveal how the universe inspires a profound and transformative awe within us. You will gain a new perspective on your place in the grand scheme of everything. We will venture from the birth of the universe in a fiery flash to the mysterious, invisible forces shaping its destiny. What is it about the silent, starry void that speaks so directly to the human soul? This feeling is something far deeper than simple wonder. It is a specific, profound emotion we call awe. Picture the breathtaking moment you first stand at the rim of the Grand Canyon, dwarfed by its immense scale and ancient history. Now multiply that feeling by the countless galaxies scattered across the cosmos. That is cosmic awe. It is not just surprise or curiosity. It is a complex emotional response triggered by two key ingredients: perceived vastness and a need for mental accommodation. Vastness is the sheer, incomprehensible scale of what you are contemplating, from the distances between stars to the age of the universe itself. The need for accommodation is your mind struggling to update its understanding of the world to fit this new, staggering reality. Psychologists have studied this powerful feeling, finding that experiences of genuine awe can make us more humble and increase our sense of connection to others and the world around us. It shrinks the ego while expanding our perspective. This very emotion has been a silent partner to human progress for millennia. It is the driving force that compelled ancient astronomers to map the heavens and inspired poets to write about the stars. It is the spark behind both scientific discovery and artistic expression, a universal human response to the infinite. So, when was the last time the universe made you feel small, yet strangely significant? That poignant mixture of humility and belonging is the emotional foundation of our cosmic curiosity, a legacy written in the stars that now calls us to look back through time. Long before the first telescope, the Babylonians meticulously tracked the wanderings of planets against a backdrop of fixed stars. They carved their observations into clay tablets, creating the earliest known astronomical records with nothing but their eyes and relentless curiosity. This drive to comprehend the heavens was a human constant, echoing across the globe. The Maya built precise calendars aligned with celestial cycles, while Greek poets saw the constellations as heroes and beasts immortalized in the night. For these cultures, the cosmos was not a cold void but a living narrative, a divine tapestry woven with stories that explained their world and their place within it. This worldview, with Earth as the unmoving center of creation, provided comfort and order for centuries. Then came a revolution not just of science but of spirit. The proposal that Earth revolved around the sun, championed by thinkers like Copernicus and Galileo, did more than correct a scientific error. It launched a philosophical shockwave that displaced humanity from the center of the universe. We were no longer the stage for a cosmic drama, but merely inhabitants of one world among many. This was a humbling, awe-inspiring reorientation. Galileo, peering through his telescope at the jagged surface of the moon and the moons of Jupiter, wrote of being overwhelmed by the grandeur of the celestial realm. Johannes Kepler, deciphering the elliptical orbits of planets, spoke of reading the thoughts of God in the geometry of the heavens. Their wonder was not detached, it was a passionate, almost spiritual response to revelation. For our ancestors, awe was inseparable from fear of the gods, the solace of religion, and a deep, persistent desire to find meaning in the great expanse above. This historical journey reveals that our cosmic fascination is an ancient, timeless thread in the human story, a thread that would soon be pulled by new inventions that finally brought the distant cosmos into clear view. Galileo's simple spyglass revealed something impossible: 4 tiny stars huddled near Jupiter that shifted position night after night. He was not seeing stars but worlds, moons orbiting another planet. This single observation shattered the ancient belief that everything in the heavens revolved around Earth. It was a quiet revolution in a Venetian garden, proving we were just one destination in a much larger celestial dance. That humble tube of wood and glass was the first true window to infinity, and we have been building better windows ever since. From Galileo's first lenses to the colossal mirrors of modern observatories, each technological leap has peeled back another layer of the cosmos. We built radio telescopes to listen to the silent songs of distant gas clouds, and X-ray telescopes to witness the violent deaths of stars in brilliant bursts of energy. Each type of eye gives us a different piece of the universal puzzle, yet their most profound power is not just to see across space, but to see back in time. Every telescope is a time machine. When you look at the light from a star 1,000 light-years away, you are seeing it not as it is now, but as it was 1,000 years in the past. You are witnessing ancient history directly. This principle reaches its most breathtaking conclusion with the Hubble Space Telescope. Astronomers once pointed Hubble at what seemed to be a completely empty patch of sky, a dark void no larger than a grain of sand held at arm's length. For days it collected the faintest trickles of light. The resulting image, called the Hubble Deep Field, did not show emptiness. It revealed a universe crammed with glory, a splash of thousands of galaxies, each a swirling island of billions of stars. That single image captured a core sample of the cosmos, a narrow shaft drilled deep into space and time, revealing galaxies as they were when the universe was young. This is the legacy of the telescope, a tool that transforms abstract wonder into tangible discovery. It has opened a door not merely to distant worlds, but to the very origin of everything, inviting us to witness the moment of creation itself. That single, profound question leads us back, past the most ancient galaxies, to the very beginning. The ultimate origin story begins with a mystery that defies common sense: the concept of the entire universe emerging from a single point of infinite density and temperature. This was the singularity, a state where all the laws of physics as we know them break down. Then, in an event we call the Big Bang, this point underwent an unimaginable expansion, not into space but of space itself. Time, as we measure it, began its relentless forward march at that very instant. To grasp this, picture the entire universe as the surface of a balloon. As you inflate it, every point on that surface moves away from every other point. The galaxies are not racing through space on the balloon. They are embedded within the fabric of the balloon as it stretches. This is the expansion of our cosmos, a creation of space and time from a single, unfathomable origin. The physicist Stephen Hawking famously wrestled with the implications of this beginning, suggesting that asking what came before the Big Bang is like asking what is north of the North Pole. The question itself may lose its meaning as time, as we understand it, did not exist. This is not just a scientific model, it is a narrative that reshapes our understanding of reality. And like any good story, it is supported by evidence. The most compelling proof comes from a faint, cold glow that permeates all of space, the cosmic microwave background radiation. This is the afterglow of the Big Bang itself, cooled and stretched by the expansion of the universe over billions of years, a relic from when the cosmos was a searing hot plasma. It is the oldest light we can see, a baby picture of the universe. So what does it mean for our existence that everything, from the stars to our own bodies, traces back to a definitive starting point? It means we are not just in the universe, we are a product of its history, stardust forged in a cosmic fire that had a first moment. Understanding this explosive birth sets the stage for examining the very building blocks of reality that were cast out from that initial fire. That initial fire forged everything we see, yet it accounts for less than 5% of the cosmos. The true nature of the universe is dominated by mysteries, and the greatest of these is dark matter. This is the invisible glue, an unseen scaffold that holds galaxies together against the immense centrifugal forces of their own spin. We cannot see it, touch it, or detect it with any conventional telescope, yet we know it must be there because of its profound gravitational pull on the things we can see. The story of its discovery begins not with a flash of light, but with the meticulous work of astronomer Vera Rubin. She was studying the rotation of spiral galaxies, expecting to find that stars on the outer edges, like our own solar system in the Milky Way, would move slower than those near the bright, dense center. This is simple orbital mechanics, the same reason Pluto takes far longer to orbit the Sun than Mercury does, but her observations revealed something astonishing. The stars at the galactic outskirts were racing around just as fast as those near the core. According to all known physics, these galaxies should have been flying apart, their outer stars flung into the void by their own speed. The only possible explanation was that each galaxy was embedded within a massive, invisible halo of something, a substance exerting extra gravity to hold the entire structure together. This something is what we now call dark matter. Current theories suggest it could be composed of exotic particles, with one leading candidate known as WIMP, or weakly interacting massive particles. As the name implies, these hypothetical particles would interact with normal matter only through gravity and the weak nuclear force, making them fantastically difficult to catch. Think of it like standing in a forest on a perfectly calm day. You cannot see the wind, but you can see its undeniable effect as the tops of the trees sway and rustle. You are witnessing the evidence of an invisible force. Dark matter is the cosmic wind, and the swirling motion of galaxies is the rustling of the trees. This mysterious substance is not a minor component of reality. It makes up about 27% of the universe, outmassing all the stars, planets, and nebulae combined by a factor of more than 5 to 1. Its gravitational pull is the primary architect of the cosmic web, the vast structure upon which galaxies are strung like glittering pearls. The profound challenge is that after decades of searching with exquisitely sensitive detectors placed deep underground to shield from cosmic noise, we have not directly detected a single dark matter particle. This enigma stands as a monumental challenge to our understanding of physics, a silent testament that the universe is built from something far stranger than we ever dreamed. But if dark matter is the cosmic glue, an even stranger force is acting as cosmic anti-gravity. The universe is not just expanding, it is accelerating. This discovery was so shocking it overturned a fundamental assumption in cosmology. For decades, astronomers believed the mutual gravitational pull of all the matter in the cosmos would eventually slow the expansion from the Big Bang, perhaps even reverse it in a big crunch. Then, in the late 1990s, two independent teams were observing distant stellar explosions called Type 1, a supernova. These explosions are standard candles, meaning they have a known intrinsic brightness. By measuring how dim they appear from Earth, scientists can calculate their distance with remarkable accuracy. The teams expected to find that the most distant, and therefore oldest, supernova were receding faster than nearby ones, a sign of the initial expansion. But they found something else entirely. The most ancient explosions were dimmer than they should have been, meaning the space between us and them had stretched more than anyone predicted. The expansion of the universe was not slowing down, it was speeding up. This was like tossing a ball into the air and watching it fly away from you faster and faster, defying gravity itself. The discovery earned the team leaders the Nobel Prize in Physics in 2011 and introduced the world to its dominant component, dark energy. The leading explanation for this accelerating force reaches back to an idea Albert Einstein once called his greatest blunder. He called it the cosmological constant, a repulsive energy inherent to the fabric of empty space itself. This is the energy of the vacuum, a seething sea of virtual particles that pop in and out of existence, borrowing energy from nothing for fleeting moments. This vacuum energy exerts a negative pressure, pushing space itself apart. While Einstein originally introduced the concept to force his equations to describe a static universe, he abandoned it after Hubble discovered the expansion. Now it has made a triumphant and puzzling return. The problem is one of scale. When physicists calculate how much energy this quantum vacuum should contain, the number is astronomically, impossibly large. It should be 120 orders of magnitude stronger than what we observe. This is the widest discrepancy between theory and experiment in all of science. So what is dark energy? We simply do not know. It could be Einstein's cosmological constant, a steady force woven into space-time, or it could be a dynamic field that changes over time, known as quintessence. Its true nature remains one of the greatest puzzles in physics. This mysterious force now dictates the ultimate fate of the cosmos. If dark energy remains constant, as the cosmological constant suggests, the universe will continue its accelerated expansion forever. Galaxies will be pulled apart from one another, their light stretched beyond the visible spectrum. Star formation will cease as gas clouds are torn asunder, and the universe will drift toward a cold, dark, and empty end known as the Big Freeze or heat death. But if dark energy strengthens over time, a more dramatic and violent finale awaits, the Big Rip. In this scenario, the repulsive force would eventually overcome all other forces in the universe. First, galaxy clusters would be torn apart, then individual galaxies. As the end approaches, stars would be ripped from their solar systems and planets from their stars. In the final moments, even atoms and atomic nuclei would be shredded by the overwhelming expansion of space itself. The universe would end not with a crunch, but with a silent, fundamental tear in the fabric of reality. This cosmic destiny, driven by an invisible energy we cannot yet explain, connects the grandest scale of the cosmos to the strange, uncertain behavior of the quantum world. It is a humbling reminder that the universe is not only stranger than we imagine, but stranger than we can imagine. This strange quantum reality is not confined to laboratories. It breathes life into the cosmos itself. Inside the crushing heart of a star, the process of nuclear fusion relies on a quantum trick called tunneling. For two protons to fuse, they must overcome a powerful barrier of electrical repulsion, like trying to roll a ball over a mountain without the energy to reach the top. Classically, it is impossible, but in the quantum world, particles are not just balls, they are also waves of probability. There is a finite, if small, chance that a proton will simply disappear from one side of the energy mountain and reappear on the other, effectively tunneling through the barrier. Without this quantum loophole, stars would not shine, and the elements essential for life would never have been forged. This bizarre behavior extends to the very vacuum of space. According to quantum field theory, what we call empty space is not empty at all. It is a seething, bubbling foam where virtual particles and their antiparticles constantly pop into existence out of nothing, borrowing energy from the universe for an impossibly brief moment before annihilating each other. This quantum frenzy, this energy of nothing, might be the very source of the dark energy that is tearing our universe apart. So how does the quantum realm, so infinitesimally small, command such influence over the cosmic, so vast? The answer may lie in the first moments of the Big Bang, when the entire universe was compressed into a volume smaller than an atom. In that primordial seed, quantum fluctuations were not tiny. They were everything. As space expanded violently, those microscopic random jitters were stretched to astronomical sizes, becoming the gravitational seeds for all future structure. The vast cosmic web of galaxies, with its great walls and immense voids, is a fossilized imprint of quantum noise from the dawn of time. Your existence, and the existence of every galaxy, can be traced back to a random twitch in the quantum foam. This profound connection between the smallest and largest scales brings us to the ultimate frontier, a place where even the concepts of space and time begin to unravel. At the very edge of a cosmic waterfall, space and time themselves flow inward, past a boundary from which not even light can climb back out. This is the event horizon of a black hole, the ultimate point of no return. These gravitational monsters are not born from malice, but from the spectacular death of a giant star. When a star many times more massive than our Sun exhausts its nuclear fuel, the outward pressure that sustained it for millions of years vanishes in an instant. Its own immense gravity, no longer opposed, causes the core to collapse catastrophically. In a matter of seconds, an object the size of a city is crushed into a point of infinite density, a singularity. The spacetime around this point warps so severely that it punches a hole in the fabric of the universe, creating a black hole whose gravitational pull dominates everything in its vicinity. For decades, black holes existed only as mathematical predictions and artistic interpretations. Then, in April 2019, a global collaboration of telescopes known as the Event Horizon Telescope presented the world with the first direct visual evidence. They revealed the shadow of the supermassive black hole at the heart of the galaxy Messier 87, a dark silhouette encircled by a fiery ring of superheated gas swirling at near light speed. That haunting image was not of the black hole itself, for no light can escape it, but of its event horizon, the shadow it casts upon the bright backdrop of its own accretion disk. It was a monumental achievement, confirming a century-old prediction and giving a face to one of the most elusive objects in the cosmos. Yet, even these cosmic vacuums are not entirely black. Theoretical physicist Stephen Hawking made a startling discovery, merging quantum mechanics with gravity to propose that black holes can, in fact, evaporate. The mechanism is as strange as the objects themselves. Remember the seething quantum foam of virtual particles that pop in and out of existence. At the very precipice of the event horizon, one of a particle-antiparticle pair might fall in while the other escapes. The escaped particle carries away a tiny bit of the black hole's mass, appearing to an outside observer as a faint emission, now known as Hawking radiation. Over trillions upon trillions of years, this slow leak would cause a black hole to gradually shrink and presumably vanish. This elegant theory, however, creates one of the most profound puzzles in modern physics, the information paradox. According to quantum mechanics, information about what falls into a black hole, whether it was a star, a planet, or a library of books, can never be truly destroyed. But if the black hole evaporates completely, radiating only random heat, what happens to all that information? Is it lost forever, violating a fundamental law of the universe? Or is it somehow encoded in the Hawking radiation, preserved in a way we cannot yet decipher? This paradox forces us to question the very nature of reality and whether our current laws of physics are complete. Black holes are the universe's ultimate laboratories, stretching our concepts of space, time, and information to their breaking point. They challenge us to consider what truly lies beyond the event horizon, and whether the singularities at their hearts might be gateways to other realms or other universes entirely. They are not merely destructive ends, but perhaps the key to a deeper understanding, pushing us to the precipice of knowledge and inviting us to peer into the ultimate unknown. Beyond the horizon of our own universe, a far grander possibility emerges. What if our cosmos is not the entire story, but merely a single chapter in an infinite library of realities? This is the Multiverse Hypothesis, a speculative but compelling idea that our universe is just one bubble in a vast, bubbling cosmic foam. Picture a pot of water coming to a boil. Each bubble that rises to the surface is a self-contained universe, inflating from its own Big Bang and potentially operating under a completely different set of physical laws. In one bubble, gravity might be 10 times stronger, making planets impossible. In another, the nuclear forces might be too weak to allow atoms to form. Our universe, with its precise, life-permitting constants, could simply be one of the rare bubbles where the conditions were just right. This concept finds support in two leading theoretical frameworks. The first is eternal inflation, an extension of the Big Bang theory which suggests that the rapid expansion of spacetime never truly stopped everywhere. Instead, it continues eternally in a background sea of energy, with new universe bubbles constantly nucleating and budding off from this inflating substrate. The second framework is string theory, which attempts to unify all forces and particles by proposing that the fundamental constituents of reality are tiny, vibrating strings. String theory, however, requires extra dimensions of space to work mathematically, and it predicts a colossal number of possible stable configurations for those dimensions, perhaps 10 to the 500 different versions. Each stable configuration could correspond to a different universe with its own unique physics. The physicist Brian Greene has eloquently framed the staggering implication, suggesting that if the multiverse is real, then the reason we find ourselves in a universe fine-tuned for life is not a miracle, but a simple consequence of probability. With an infinite number of universes, every possible set of conditions will be realized somewhere. We, of course, can only exist in one of the rare ones that allows for our presence. This is a deeply humbling thought. It transforms our cosmic home from a uniquely crafted stage into a single, fortunate ticket in an infinite cosmic lottery. The greatest challenge, of course, is one of evidence. How can we ever test for the existence of other universes, sealed off from our own by the ultimate horizon of their separate spacetime? Some scientists speculate that if two bubbles collided in the distant past, the imprint of that colossal impact might be faintly visible in the cosmic microwave background, a scar on the oldest light in our sky. Others suggest that the strange, large-scale features we see in the distribution of galaxies could be hints of such a collision. For now, these remain tantalizing possibilities, pushing the very definition of science to its limit. This expansion of the infinite into the plural makes our existence feel both profoundly special and utterly commonplace. It directly echoes the next great cosmic question. If an infinite array of physical realities is possible, then how common is the phenomenon we call life? On August 15, 1977, a radio telescope in Ohio recorded a signal so powerful and unusual that the astronomer who discovered it circled the printout and wrote one word in the margin: wow. For 72 seconds, a narrowband burst of intense radiation, perfectly aligned with the predicted frequency of interstellar hydrogen, seemed to come from the direction of the constellation Sagittarius. It was never detected again. That single, tantalizing event captures the essence of our deepest cosmic question, a question that echoes across the millennia: are we alone? This is not a modern query. The ancient Greek philosopher Metrodorus of Chios speculated that for a single ear of wheat to grow in a large field would be no more strange than for a single world to bear life in the infinite universe. Today, we have moved from pure speculation to a scientific search, a quest to find our place in a biological cosmos. To frame this search, the astronomer Frank Drake devised a simple yet profound way to estimate the number of civilizations we might potentially contact. The Drake equation breaks down this grand unknown into a series of manageable variables. It begins with the rate of star formation in our galaxy, then multiplies that by the fraction of stars that have planets. Next, it considers the number of those planets that are habitable, where conditions could allow for liquid water. The equation then moves into more uncertain territory, estimating the fraction where life actually emerges, where that life becomes intelligent, and where that intelligence develops the technology to communicate across the stars. Finally, it accounts for the length of time such a civilization might last before fading away. Plugging in optimistic numbers can suggest a galaxy teeming with voices, while conservative estimates can paint a picture of profound, eternal silence. The equation is not a calculation with one right answer, but a framework for our ignorance, a map of everything we still need to learn. Our methods for filling in that map are as ingenious as they are diverse. Giant radio telescopes like the Allen Telescope Array systematically scan the sky, listening for the faint whisper of an artificial signal amidst the natural radio roar of the cosmos. We are also learning to read the light from distant worlds. When an exoplanet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere. By analyzing that filtered light with instruments like the James Webb Space Telescope, we can detect the chemical fingerprints of gases like oxygen, methane, and carbon dioxide. The simultaneous presence of such gases, which on Earth are produced by life, could be a powerful biosignature, a hint of a living world. Consider the TRAPPIST-1 system, a compact family of 7 Earth-sized worlds orbiting a cool red dwarf star 39 light-years away. 3 of these planets reside in the star's habitable zone, the region where temperatures could be just right for liquid water. While the harsh environment of a red dwarf poses challenges, this system represents a stunning abundance of potential real estate for life, all within a single stellar neighborhood. Our search is not only focused on the distant heavens, but also on our immediate planetary neighbors. The Perseverance rover is currently rolling across the ancient lakebed of Mars's Jezero crater, its robotic arms drilling into rock to collect samples. Its mission is to seek signs of past microbial life, fossilized evidence that Mars was once a wetter, warmer world where life could have gained a foothold. Each scoop of regolith is a page from a history book 4 billion years old, a direct investigation into whether biology is a universal phenomenon or a singular earthly miracle. The quest to find another living world is about more than just biology, it is about our cosmic identity. Carl Sagan profoundly expressed that if we are alone in the universe, it would be an awful waste of space. The discovery of even a single, humble microbe on another world would irrevocably change everything. It would tell us that the genesis of life is not a miracle, but a natural process, a cosmic imperative. The universe would become a living, breathing place brimming with potential. So how would the confirmed knowledge that we are not alone reshape our perspective on humanity? Would our ancient tribal divisions on Earth seem smaller, more trivial, under the shared banner of being one form of life among many? This search for company in the cosmos is the ultimate extension of our awe, a desire to connect our tiny story to a grand biological narrative. It inspires us not only to look outward, but to look back at our own vibrant, fragile world with a renewed sense of responsibility and wonder. That search for life beyond our world inevitably brings our focus back to the one place we know it exists. In February 1990, from a distance of 4 billion miles, the Voyager 1 spacecraft was commanded to turn its camera homeward for one last time. The image it captured showed not continents or blue oceans, but a tiny, pale blue dot suspended in a sunbeam. It was a mote of dust, as Carl Sagan would later reflect, a speck in the immense cosmic dark. In that single frame, all of human history, every war and discovery, every triumph and heartbreak, was contained on that barely visible pixel. Sagan's reflection on this image remains one of the most powerful evocations of our true circumstance. He noted that everyone you love, everyone you know, every human being who ever was, lived out their lives on that speck. All our joy and suffering, every king and peasant, every cherished belief, is confined to this tiny stage in a great cosmic arena. This perspective does not diminish our world, but elevates its profound fragility and unity. Our planet is a perfect and perfectly rare sanctuary. Its atmosphere acts as a protective blanket, shielding us from the sun's harsh radiation while trapping just enough heat to maintain liquid water. Our magnetic field, generated by a churning molten core, deflects lethal solar winds that would otherwise strip away that precious air. A stable orbit around a benevolent star keeps our climate within a narrow, life-sustaining range. These are not mere coincidences. They are the delicate, interconnected systems that allow the phenomenon of life to flourish. Yet, our time on this sanctuary has given rise to a new geological epoch, the Anthropocene, an era defined by humanity's overwhelming impact on the planet's systems. For the first time in Earth's history, a single species is consciously altering the climate, reshaping the landscapes, and directing the flow of elements. This power comes with a profound responsibility, a duty of stewardship for our only home. This shift in awareness is not just philosophical, it is physiological. Astronauts who have seen Earth from orbit often report experiencing the overview effect, a cognitive shift in consciousness. From that vantage point, national borders vanish. The atmosphere appears as a shockingly thin, fragile lens against the black void. The interconnectedness of all life and systems becomes an undeniable, visceral truth. The astronaut Ron Garan described it as seeing the world without any divisive lines, understanding that we are all in this together, riding through the universe on this beautiful, fragile spaceship. That is the ultimate ground for our cosmic awe. The infinite tales of black holes, dark energy, and the multiverse all lead us back to this single, stunning realization. Our planet is an oasis of unimaginable rarity and beauty in a cosmos that is largely cold, empty, and hostile to life as we know it. Gazing outward at the grand mysteries ultimately inspires us to look inward, to protect the pale blue dot that is our entire world. Our fragile world, and everything on it, is built from elements forged in the heart of distant, long-vanished suns. The very iron in your blood, the calcium in your bones, and the oxygen you breathe were all created in the fiery lives and explosive deaths of stars. This is the story of cosmic recycling, a grand cycle of creation that begins in the cold, dark nurseries of space. Vast clouds of gas and dust, called nebulae, drift for eons until a passing shockwave from a dying star compresses a pocket of this material. Under the relentless crush of its own gravity, the cloud begins to collapse, spinning faster and growing hotter at its core. When the temperature and pressure reach a staggering 15 million degrees, a miracle of physics ignites. Hydrogen atoms are forced together, fusing into helium and releasing a torrent of energy in a process called nuclear fusion. A star is born. Our own Sun is a middle-aged, humbly sized star in the midst of this stable phase. For billions of years, the outward pressure from its core fusion has perfectly balanced the inward pull of its immense gravity. This equilibrium is the engine of our solar system, bathing our world in the steady light and warmth that makes life possible. But this stability is temporary. A star's destiny is written in its birth weight. The most common stars in the universe, red dwarfs, are so small and frugal they may burn for trillions of years, eventually fading to a cold, dark cinder. Middleweight stars like our Sun have a more dramatic finale. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. Its outer layers will expand violently, engulfing the inner planets and transforming our star into a bloated red giant. Eventually, these outer layers will drift away, forming a beautiful planetary nebula, a glowing shroud of gas illuminated by the dying ember at its center. All that will remain is the Sun's incredibly dense, Earth-sized core, a white dwarf. This stellar corpse will glow with residual heat for billions of years before cooling into a black diamond in the void. The most massive stars live fast and die young. Their immense gravity creates furnaces so intense that they can fuse elements all the way up to iron. But iron fusion consumes energy instead of releasing it. With its power plant suddenly shut down, the star has no defense against its own gravity. The core collapses in less than a second, triggering a cataclysmic rebound explosion known as a supernova. For a few brilliant weeks, a single dying star can outshine an entire galaxy. The violence of this explosion is the universe's primary forge, creating every element heavier than iron, from the gold in a wedding ring to the uranium that powers nuclear reactors. Astronomer Carl Sagan captured this profound connection perfectly when he wrote, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars." We are made of star stuff. Every time you look up at the night sky, you are looking at the very factories that built you. These stellar explosions do not just create elements, they blast them across space, seeding future generations of stars and planets. The cosmic dust from a supernova, mixed with the remnants of planetary nebulae, eventually coalesces into new nebulae where the cycle begins again, giving rise to new stars, new worlds, and perhaps new life. This endless story of stellar life and death is the foundational process that fills the cosmos with the raw materials for planets and sets the stage for the next great wonder, the formation of worlds around these stellar engines. Before 1995, our solar system was the only planetary family we knew. That changed dramatically with the announcement of a world orbiting a star called 51 Pegasi, a discovery that ripped up the astronomy textbooks. This was not a cold, distant rock, but a gas giant hugging its sun so closely that its year lasted a mere 4 Earth days. Astronomers had found the first planet around a sun-like star, proving that other solar systems not only existed, but could be wildly different from our own. This single discovery flung open a cosmic door, launching a golden age of exploration for alien worlds. We find these distant specks not by seeing them directly, but by watching for the subtle clues they leave on their host stars. One primary method is the transit technique. Imagine walking past a streetlight and noticing its glow dim ever so slightly as a moth flutters across the bulb. On a cosmic scale, a distant star's light dips in a predictable, repeating pattern when one of its planets passes in front of it. This tiny eclipse reveals the planet's size and the length of its year. Another method, radial velocity, watches for a star's wobble. A star and its planet actually orbit a common center of gravity, meaning the star makes a tiny, rhythmic dance as the planet's gravity tugs on it. By measuring the subtle color shifts in the star's light as it moves toward us and away from us, astronomers can deduce the planet's mass. The treasure trove of data from missions like the Kepler Space Telescope has unveiled a staggering diversity of worlds that defy simple categorization. We have found hot Jupiters, gas giants broiling in the furnace of their suns, with years shorter than a week. We have discovered super-Earths, rocky planets larger than our own, which have no direct counterpart in our solar system. We have even found planets orbiting two stars at once, just like the fictional Tatooine, casting multiple shadows on their own moons. The ultimate goal, of course, is to find a world like our own, a planet orbiting within its star's habitable zone. This is the orbital sweet spot, often called the Goldilocks zone, where temperatures are just right for liquid water to potentially exist on the surface. Not too hot, not too cold, but just right for the chemistry of life as we know it. The Kepler mission gave us thrilling candidates like Kepler 1860f, the first Earth-sized planet found orbiting within the habitable zone of a distant star. Even closer to home, just 4.2 light-years away, is Proxima Centauri b, a rocky world orbiting the closest star to our Sun, and it too resides in that tantalizing region. While the harsh flares from its red dwarf star pose challenges for its atmosphere, its very existence so nearby ignites our imagination. These are not just points of light on a graph, they are entire new categories of planets, each with its own unique story of formation and climate. They expand our sense of cosmic possibility, forcing us to reconsider what a planet can be and where life might take root. The sheer variety hints at an almost limitless gallery of cosmic environments, each a new experiment in geology, chemistry, and perhaps even biology, waiting for us to learn how to look more closely. These vast, colorful clouds are far more than just cosmic scenery. They are the cradles and the graves of stars, the engines of cosmic rebirth. The most famous of these, the pillars of creation, stand like colossal, ghostly sentinels in the Eagle Nebula. Captured in breathtaking detail by the Hubble Space Telescope, their towering forms are not solid, but dense, light-year-high columns of cold gas and dust, glowing with the fierce light of newborn stars eating away at their very substance. This is a stellar nursery, a place of both creation and destruction happening on an unimaginable scale. These nebulae come in several distinct types, each with its own story. Emission nebulae, like the Great Orion Nebula, are vast clouds of hydrogen gas heated by the intense ultraviolet radiation from nearby young stars. They glow with their own light, shining in brilliant shades of red and pink like a cosmic neon sign. Reflection nebulae, in contrast, do not generate their own light. Instead, they act like cosmic fog, their dust particles simply reflecting the starlight from nearby suns, often casting a beautiful, ethereal blue hue. And then there are the dark nebulae, the most ominous of all. These are cold, dense clouds of dust so thick they completely block the light from the stars behind them, creating apparent voids and silhouettes against the brighter galactic background. They are the cosmic shadows, the raw, unlit material waiting for a trigger. That trigger is often the shockwave from a nearby supernova, the death of one star serving as the midwife for the next generation. This wave of pressure slams into a dark nebula, compressing pockets of gas and dust. Under the growing force of its own gravity, a single pocket begins to collapse, spinning faster and faster, flattening into a disk. At the heart of this swirling chaos, the core grows hotter and denser, a protostar taking shape. For millions of years, this process continues, the core temperature climbing until it reaches a critical threshold of about 15 million degrees. At that moment, the force of the collapse is met with an equal and opposite force from within. Hydrogen atoms are slammed together with such violence that they fuse into helium, releasing a titanic burst of energy. Nuclear fusion ignites, a new star is born, and its stellar wind blows away the remaining cocoon of gas, revealing its light to the cosmos. The poet Alfred Lord Tennyson, gazing at the Milky Way, wrote of seeing the heavens fill with commerce, argosies of magic sails, and pilots of the purple twilight dropping down with costly bales. He saw the nebulae not as simple clouds, but as vessels of immense, mysterious activity. Centuries later, scientists using Hubble see the same thing, not with poetic fancy, but with empirical clarity, watching the very process of stellar birth unfold. This cycle is the great recycler of the cosmos. The nebulae are seeded with the heavy elements forged in supernova, the iron and oxygen and carbon that are the building blocks of planets and life. From the ashes of dead stars and new worlds are born. These ethereal structures are the ultimate canvases of creation, painting a picture of constant cosmic renewal that connects the explosive death of one star to the brilliant dawn of another, and ultimately to our own existence. An apple falling from a tree inspired Isaac Newton to formulate a law of universal gravitation, a force that pulls objects together across the vast emptiness of space. For centuries, this was the accepted picture, a dependable force acting instantaneously across any distance. Then came a young patent clerk named Albert Einstein, who dared to reimagine gravity itself. He engaged in a series of brilliant thought experiments, picturing himself in a falling elevator. In that elevator, if you dropped a set of keys, they would appear to float beside you as if gravity had vanished. Einstein realized there was no experiment you could perform inside that freely falling box to prove you were in a gravitational field. This equivalence between acceleration and gravity was the key that unlocked a new cosmic truth. Einstein proposed that gravity is not a force pulling through space, but a warp in the very fabric of spacetime. Think of spacetime as a taut, flexible rubber sheet. The Sun, a massive object, sits in the center of this sheet, creating a deep, funnel-shaped dip. The Earth, a smaller marble, rolls around the rim of this dip, not because a mysterious force is pulling it, but because it is following the curved path, the groove created by the Sun's mass. This is general relativity. The planets orbit not because they are tugged by the Sun, but because they are traveling along the contours of a warped stage. This revolutionary idea made stunning predictions. Einstein suggested that light itself, traveling through this warped spacetime, would not always move in a straight line. The gravity of a massive object like a galaxy cluster could bend the light from a more distant star, acting as a cosmic magnifying glass. This phenomenon, called gravitational lensing, was first confirmed during a solar eclipse in 1919, when stars near the Sun appeared slightly out of place, their light bent by the Sun's gravity. Decades later, an even more dramatic confirmation arrived. Einstein's theory also predicted that cataclysmic cosmic events, like the collision of two black holes, would send ripples through the fabric of spacetime itself. These gravitational waves would stretch and compress space as they traveled outward at the speed of light. For a century, this was just a mathematical curiosity. Then, in 2015, the LIGO Observatory detected the faint chirp of two black holes merging over 1 billion light-years away, a direct measurement of the universe ringing like a bell. When news of the eclipse confirmation reached him, Einstein expressed a feeling of awe and wonder that his abstract equations could so perfectly capture the behavior of the cosmos. His revolution showed that the universe is not just stranger than we suppose, but that its deepest workings can be described by the most elegant and mind-bending ideas. This profound connection between human thought and cosmic reality sets the stage for contemplating the grandest question of all, the ultimate fate of everything. The entire 14 billion-year history of the universe can be compressed into a single calendar year. On this cosmic calendar, the Big Bang strikes at the very first second of January 1st. Our Milky Way galaxy does not begin to form until around March. Our solar system and the Earth itself emerge in early September. The entire sprawling saga of human civilization, from the first cities to the dawn of the space age, all unfolds in the final minute of December 31st. This profound scaling reveals our moment as a fleeting, brilliant spark in an immense journey. The first epoch after the initial explosion was a period of unimaginably rapid expansion called inflation, where the universe grew from smaller than an atom to the size of a galaxy cluster in a fraction of a second. For the next several 100,000 years, the universe was a searing, opaque fog of plasma, so dense that light could not travel freely. Then, a pivotal event called recombination occurred. The universe had expanded and cooled enough for electrons to be captured by protons, forming the first stable hydrogen and helium atoms. Suddenly, the cosmic fog cleared. Light was set free, and that first flash of liberated light is what we detect today as the cosmic microwave background, the afterglow of creation. This ushered in the cosmic dark ages, a time of profound blackness before the first stars ignited. The universe was a vast, dark sea of neutral gas, with no sources of light for hundreds of millions of years. Gravity slowly worked its magic, pulling denser patches of this primordial gas into collapsing clouds. When the first protostars finally reached critical mass and ignited their nuclear furnaces, they ended the darkness in a dramatic dawn. These first stars were not like our Sun. They were behemoths, hundreds of times more massive, burning ferociously bright and blue, and dying young in colossal supernova. Their intense ultraviolet radiation then began to tear apart the surrounding neutral hydrogen gas in a process called reionization, relighting the cosmos and making the universe transparent to light once again, this time forever. We are not just theorizing about these ancient events, we are observing them directly. When we point our most powerful telescopes at the faintest, most distant galaxies, we are looking billions of years back in time, witnessing these very first generations of stars and galaxies as they were forming. The James Webb Space Telescope is now peering into this epoch of reionization, capturing the dim, red-shifted glow of the universe's infant galaxies, seeing further back than ever before. Future observatories like the planned Louvre telescope will push even deeper, potentially witnessing the dark ages themselves, a time before starlight existed. This entire historical perspective, from the first flash to the first star, grounds our existence in a grand, unfolding narrative. We are living in the wake of that first dawn, our lives made possible by the elements forged in those primordial stellar explosions. To see this timeline is to understand that we are not just living in the universe, we are a momentary expression of its long and ongoing story, a story whose next chapters we are only just beginning to read. Our universe appears to be built on a set of fundamental numbers that seem almost too good to be true. The force of gravity, the strength binding atomic nuclei, the rate of the universe's expansion, each of these forces is defined by a specific constant, a fixed number in the cosmic equation. What is truly staggering is how precariously balanced these numbers are. Imagine a vast control panel for the cosmos with dozens of finely calibrated dials, each governing one of these fundamental constants. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long ago. If it were slightly weaker, galaxies and stars could never have condensed from the primordial gas. If the strong nuclear force, the glue that holds protons and neutrons together, were just a few percent different carbon atoms, the essential backbone of life as we know it would never have formed inside stars. The universe would be a boring soup of hydrogen and helium, or a sea of inert iron. This is the fine-tuning problem, the observation that the constants of nature appear to be exquisitely balanced on a razor's edge, permitting the existence of complex life. This profound observation leads directly to a philosophical idea known as the anthropic principle. In its weak form, the principle is almost a tautology. It states that we can only observe a universe that is compatible with our existence as observers. If the constants were not just right, we would not be here to notice. The strong form of the anthropic principle, however, is far more provocative. It suggests that the universe must have properties that allow life to develop within it at some stage in its history, implying a kind of cosmic bias toward consciousness. This idea has sparked intense debate among physicists and philosophers. For some, like the physicist Freeman Dyson, the fine-tuning felt like the universe in some sense must have known we were coming. For others, it is not evidence of design but a calling card for the multiverse. In an infinite multiverse, every possible set of physical constants exists somewhere. We simply find ourselves in one of the rare habitable bubbles, a statistical inevitability rather than a planned outcome. Yet another perspective views this fine-tuning as pointing toward a deeper, yet undiscovered physical theory, one that would naturally explain why the constants have the values they do. So, which is it? Does this uncanny precision hint at a universe with purpose, a cosmos intended for life? Or are we the beneficiaries of an almost impossibly lucky roll of the cosmic dice, living in the one universe that worked? This philosophical dilemma adds a profound new layer to our awe. It forces us to confront the possibility that our ability to ponder the cosmos might be more than a happy accident, that consciousness itself could be a fundamental part of the cosmic story. The universe seems to require a witness. At the quantum level, a particle does not have a definite location or state until it is measured. This is the strange heart of the observer effect, where the act of observation itself seems to crystallize reality from a cloud of possibilities. The most famous illustration of this baffling idea is Schrödinger's cat. In this thought experiment, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers the release of the poison, according to the rules of quantum mechanics. Until someone opens the box and looks inside, the atom exists in a superposition, both decayed and not decayed. Consequently, the cat is proposed to be both alive and dead, a bizarre blend of states that only resolves into one concrete reality the moment an observer peers in. This is not a statement about feline mortality, but a profound puzzle about the nature of reality itself. Does the universe remain in a hazy, undefined state until a conscious mind interacts with it? This question leads to a radical hypothesis, panpsychism. This ancient idea, now gaining traction in some modern philosophical circles, suggests that consciousness is not a late-arriving product of complex brains, but a fundamental property of the universe, as basic as space, time, and matter. In this view, everything from an electron to a human being might possess some form of primitive, subjective experience. The French philosopher René Descartes famously split the world into thinking substance and extended substance, mind and matter, creating a duality that science has struggled to reconcile ever since. Today, neuroscientists grapple with the hard problem of consciousness, the mystery of how the 3 pounds of gelatinous tissue in our skulls gives rise to the rich, inner world of subjective feeling, the redness of red or the pain of a stubbed toe. How does objective electrical activity produce subjective experience? This gap between the physical brain and the conscious mind remains one of science's greatest frontiers. Perhaps our ability to look upon the cosmos with awe is not an accidental byproduct of evolution, but a fundamental feature of a universe that is becoming aware of itself. Our comprehension of galactic spirals and quantum spins might be the cosmos's way of knowing its own story. The awe we feel when gazing at the stars is then more than a passive emotion. It is an active participation, a resonant feedback loop between the mind within and the universe without. This intimate connection, where the subjective act of observation meets the objective grandeur of the cosmos, finds its most powerful expression not in equations, but in the art and stories we have created for millennia. The hunter Orion eternally pursues the Pleiades across the night sky, a story written in starlight by the ancient Greeks. This was not a solitary act of imagination, but a universal human impulse. Across the globe, cultures looked up at the very same stars and saw entirely different narratives, each reflecting their unique worldview. The indigenous peoples of Australia saw the Milky Way not as a river of light, but as a celestial emu, its dark dust clouds forming the body of the great creator spirit from the dreamtime. In the frozen north, Norse poets sang of Yggdrasil, a colossal world tree whose roots and branches held the 9 realms of their cosmos, with the stars as sparks from the fire of Muspelheim. These were far more than just enchanting tales. They were the bedrock of civilization's first technologies. By watching the predictable dance of constellations like Orion, farmers knew when to plant and when to harvest. Polynesian navigators, guided by star paths memorized over generations, undertook epic voyages across the trackless Pacific, reading the heavens as a living map. The stars also served as a moral compass. In the ancient epic of Gilgamesh, the hero seeks immortality and is directed to a magical plant at the bottom of the sea by the celestial god Shamash. Even here, the heavens are a source of divine wisdom and a reminder of human limits. This profound need to weave the cosmos into our stories has never truly faded. The sprawling galactic empires of modern science fiction are the direct descendants of these ancient myths, using the vastness of space to explore timeless questions of power, identity, and our place in the universe. The sky has always been our first storybook, and we are still learning how to read its infinite pages. The monolith in 2001: A Space Odyssey is a silent, alien teacher, and its most profound lesson is one of scale. It marks the moment our ape ancestors first used a tool, and it later reappears orbiting Jupiter, a signpost for the next leap in human evolution. This is science fiction operating at its most ambitious, transforming the cold facts of astronomy into a grand narrative about intelligence and our place in the cosmos. From the cosmic dread of H.G. Wells to the hopeful ingenuity in The Martian, this genre is our modern mythology, building campfire tales not from wood smoke, but from quantum foam and galactic dust. Arthur C. Clarke, who co-wrote 2001, famously stated that the goal of science fiction is to prepare the human mind for the future, a future that is coming whether we are ready or not. He saw these stories as a kind of mental conditioning, allowing us to face the profound changes that contact with other intelligences or new technologies would inevitably bring. This preparation takes many forms, each with its own relationship to the awe we feel. Hard science fiction, like Andy Weir's The Martian, grounds its drama in meticulous scientific accuracy. The protagonist's struggle to survive on Mars is a series of engineering puzzles solved with real chemistry and physics, making the vast, hostile environment of another world feel tangible and conquerable. This realism does not diminish the wonder, it amplifies it, inspiring a generation of engineers and astronauts by showing a future that feels within our grasp. In contrast, space opera, like the sprawling epics of Star Wars, uses the cosmos as a backdrop for archetypal stories of good and evil. The awe here is more theatrical, found in the spectacle of alien fleets and strange worlds, reminding us that the universe is a stage large enough for any drama. Then there are the quieter, more philosophical works, like the film Arrival, which explores how contact with an intelligence utterly alien to our own would force us to rethink not just science, but the very nature of time, language, and consciousness. These stories are not predictions but provocations. They take the genuine mysteries of dark matter, quantum entanglement, and exoplanets and weave them into human-scale dilemmas. They allow us to emotionally rehearse for discoveries we have not yet made, to feel the weight of infinity before we ever leave our solar system. This narrative drive to explore the unknown through story finds a parallel in the work of artists who take the same raw data from telescopes and translate it into visual poetry that speaks directly to our sense of wonder. The same impulse that drew ancient hands to paint celestial patterns on cave walls now guides digital artists rendering nebulae in vivid color. Long before written language, our ancestors used ochre and charcoal to map the constellations they saw, etching star charts onto stone as a way to comprehend the rhythms of their world. This artistic lineage stretches unbroken through the centuries. During the Renaissance, astronomers like Johannes Kepler worked alongside artists who translated their celestial observations into intricate engravings, blending scientific precision with breathtaking beauty. These illustrations were not mere documentation, they were acts of reverence, attempts to capture the sublime order of the heavens. This tradition finds one of its most powerful expressions in Vincent van Gogh's Starry Night. The painting does not attempt a photorealistic sky. Instead, it channels the raw emotion of the cosmos with swirling, turbulent stars and a luminous crescent moon that seem to pulse with inner life. Van Gogh wrote of needing a terrible need of, shall I say the word, religion, and so I go outside at night to paint the stars. His brushstrokes capture not the cold facts of astronomy, but the overwhelming feeling of awe itself, the dizzying sensation of looking into infinity. Modern artists continue this dialogue, often using actual scientific data as their medium. Digital creators and installation artists frequently incorporate images from the Hubble and James Webb telescopes directly into their work, projecting galactic whirlpools across entire rooms or translating radio emissions from pulsars into immersive soundscapes. One artist described the process as giving a voice to the silent data, creating a bridge between the analytical mind and the emotional heart. This creative expression is a vital counterpart to the scientific pursuit. Where equations describe the force of gravity, a sculpture can make you feel its pull. Where data charts the life cycle of a star, a painting can make you mourn its death. Art takes the vast, abstract concepts of dark energy, quantum foam, and galactic collisions and makes them tangible. It allows us to experience cosmic wonder not just as an intellectual idea, but as a visceral, human response. In this way, the artist's studio and the astronomer's observatory are partners in the same grand endeavor, both seeking to translate the infinite tales of the cosmos into a language the human soul can understand. Galileo's discovery of Jupiter's moons was a quiet revolution. but it was only the first domino to fall in a chain of cosmic revelations. A century later, Isaac Newton formulated his universal law of gravitation, providing the mathematical framework that explained not only an apple's fall but the elegant orbits of planets and comets. This was a monumental leap, suggesting the entire cosmos operated on a set of knowable, predictable rules. Yet, the universe was saving its greatest surprises for the 20th century. In the 1920s, astronomer Edwin Hubble was studying faint, fuzzy nebulae. Using the powerful new Hooker telescope, he made a startling identification. These were not clouds within our own Milky Way, but entire galaxies, vast islands of stars far beyond our own. Our universe was immeasurably larger than anyone had dreamed. Hubble then noticed something even more profound. The light from these distant galaxies was stretched, shifted toward the red end of the spectrum. This redshift meant they were all moving away from us. More astonishingly, the farther away a galaxy was, the faster it was receding. This was Hubble's law, and its implication was breathtaking. The entire universe was expanding, like a loaf of raisin bread rising in the oven, with every raisin, every galaxy, moving away from every other. If you could run the film backward, you would see all that matter and energy converging to a single point, the first direct evidence for the Big Bang. Decades later, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, maddening hiss in their giant horn antenna in New Jersey. They scrubbed away pigeon droppings and checked every connection, but the faint, uniform static remained, coming from every direction in the sky. They had inadvertently stumbled upon the cosmic microwave background radiation, the cooled remnant of the universe's fiery birth. This was the afterglow of creation itself, the definitive proof that our universe had a hot, dense beginning. The next great surprise arrived at the very end of the 20th century. Two teams of astronomers were using distant supernova to measure how much the universe's expansion was slowing down due to gravity. Instead, their data revealed the opposite. The expansion was speeding up. Some mysterious repulsive force, which we now call dark energy, was stretching the very fabric of space-time at an ever-increasing rate. This discovery of the accelerating universe completely overturned our expectations for the cosmic future. Most recently, in 2015, a century after Einstein predicted their existence, the LIGO Observatory felt the universe quiver. It detected the faint chirp of gravitational waves, ripples in space-time caused by the collision of two black holes over 1 billion light-years away. For the first time, we were not just seeing the cosmos, we were listening to it, feeling its fundamental vibrations. Each of these milestones, from Galileo's spyglass to LIGO lasers, was built upon the work of those who came before. They show science as a cumulative chorus of curiosity, each discovery deepening our awe while revealing how much more remains shrouded in mystery. These grand discoveries have illuminated the cosmos, yet they have also carved out an even deeper darkness at the frontier of our understanding. We are left staring at questions that probe the very limits of reality. What, for instance, happened before the Big Bang? The concept of before may be meaningless, as time itself might have begun with that event. Perhaps our universe is one cycle in an endless series of cosmic expansions and contractions, a bouncing cosmos with no true beginning. Or maybe it is a bubble that nucleated from a larger, eternal multiverse. Each possibility stretches our intuition to its breaking point. This leads directly to the mystery of time itself. Is time a fundamental property of the universe, or merely an emergent illusion, a side effect of the increasing disorder we call entropy? We feel its relentless, one-way flow, yet the fundamental laws of physics work perfectly well in reverse. The true nature of time remains one of physics's most profound enigmas. On the smallest scales, particle physics presents its own glaring puzzle, known as the hierarchy problem. This is the bewildering question of why gravity is so unimaginably weaker than the other fundamental forces. The electromagnetic force is stronger than gravity by a factor of 10 to the power of 36. To grasp that, picture a single proton resisting the gravitational pull of the entire planet Earth. Such a vast disparity seems unnatural, suggesting a gaping hole in our current models. Physicist Nima Arkani-Hamed has spoken of this, stating that the universe is obviously trying to tell us something very important we do not yet understand. Another cosmic asymmetry defies explanation. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter, which would have promptly annihilated each other in a burst of pure energy, leaving behind a universe of light and nothing else. And yet, here we are. For every billion matter-antimatter pairs, one extra particle of matter must have survived. What was the mechanism behind this tiny, universe-saving imbalance? We have hints but no definitive answer. These are not minor gaps, they are canyons in our knowledge. The very fact that we can formulate these questions is a triumph. The physicist John Wheeler perhaps put it best when he said, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shoreline of our wonder." To stand at this shoreline is to embrace the unknown. It is to recognize that not knowing is not a failure, but an invitation. Each of these cosmic riddles is a direct summons to the curious, a challenge for the next generation of explorers to pick up the torch and venture further into the dark. The greatest tale of the infinite may be the one that has not yet been written. That human impulse to question the stars found its ultimate expression not in a lone thinker, but in a collective endeavor. The creation of NASA in 1958 was a direct response to the cosmic challenge of the space age, a national commitment to turn wonder into engineering. Its Apollo program achieved the seemingly impossible, landing humans on another world for the first time. When Neil Armstrong took that one small step onto the lunar dust, it was not just an American victory, but a leap for all of humanity, proving that our curiosity could physically carry us beyond our home planet. Across the Atlantic, the European Space Agency, or ESA, formed as a consortium of nations pooling their resources and intellect. Their Rosetta mission exemplified this collaborative spirit, a decade-long voyage that culminated in a tiny lander named Philae touching down on a speeding comet. For the first time, we were not just flying past a comet, we were riding along with one, analyzing the primordial ice that held secrets from the solar system's birth. These agencies demonstrate that the greatest cosmic mysteries are too vast for any single country to solve alone. The International Space Station stands as a towering symbol of this truth, a permanently inhabited outpost in low Earth orbit built and operated by 15 nations. In its microgravity laboratories, astronauts from around the world conduct experiments in fluid physics, materials science, and human biology that are impossible on Earth. The station itself is a testbed for the technologies we will need to journey to Mars and beyond, a shared home in the void that proves peaceful cooperation in space is not just possible but profoundly productive. The quest continues with ambitious missions now on the horizon. The James Webb Space Telescope, a partnership between NASA, ESA, and the Canadian Space Agency, is already peering deeper into the infrared universe than ever before, studying the atmospheres of distant exoplanets and witnessing the formation of the very first galaxies. Plans are actively developing for a Mars sample return campaign, an interagency effort to send a robotic fetch mission to the Red Planet, collect tubes of soil and rock cached by the Perseverance rover, and rocket them back to Earth for analysis in our most advanced labs. This would be the first round trip to another planet and our best chance to answer the ancient question of whether life ever arose beyond Earth. The technological fallout from this cosmic curiosity ripples through our daily lives. The miniature cameras in every smartphone trace their lineage to the need for small, robust imaging systems on spacecraft. The memory foam in your mattress was originally developed by NASA to improve seat cushioning and crash protection for astronauts. Advanced water filtration systems used on the space station have been adapted to provide clean drinking water in remote communities. Even the wireless headsets we use today evolved from technology created to allow astronauts to communicate hands-free. These innovations are not the primary goal of space agencies, but they are a powerful testament to how reaching for the stars forces us to solve problems in novel ways, with benefits that cascade back to Earth. By systematically transforming awe into a program of action, these organizations do more than just unlock the universe's secrets. They build a bridge between the abstract grandeur of the cosmos and the tangible progress of human society, inspiring the next generation to look up and wonder what they might discover. A vast digital universe is being mapped not just by powerful computers, but by the collective curiosity of millions. This is the world of citizen science, where anyone with an internet connection can help write the next chapter of astronomy. Projects like Galaxy Zoo invite the public to do what even the most advanced algorithms struggle with: classify the shapes of distant galaxies. By simply looking at images and answering a few questions, volunteers have helped identify rare celestial objects and unexpected galactic structures, leading to published scientific papers co-authored by the very people who spotted them from their home computers. This is not busy work, it is genuine discovery fueled by the human capacity for pattern recognition, a capacity every one of us possesses. The tradition of amateur contribution runs even deeper. Dedicated backyard astronomers, armed with increasingly affordable telescopes and sensitive cameras, routinely make vital contributions. They are the first line of defense in tracking near-Earth asteroids, their nightly observations providing crucial data on orbits that could one day protect our planet. Others meticulously monitor the light of distant stars, catching the telltale dip in brightness that signals a transiting exoplanet, data that often supplements the work of major space observatories. This collaboration is now amplified by social media and mobile apps that deliver cosmic data directly into our hands. You can receive alerts for passing satellites, monitor the sun for solar flares, or join a global network of observers through platforms that turn your smartphone into a personal planetarium. One volunteer for a meteor tracking project described the feeling of contributing as a profound shift in perspective. They said, "It is one thing to look up at the stars and feel small. It is something else entirely to log on and help count them, to know that your click is part of a global effort to understand our place in all of this." That is the true power of this movement. It transforms passive awe into active participation. You do not need a doctorate to explore the cosmos, only a spark of curiosity and the willingness to lend your eyes to the sky. This collective endeavor reminds us that the wonder of the universe is not a solitary experience, but a shared human journey. It grounds the vastness of space in the simple, powerful act of looking together, a democratization of discovery that empowers every one of us to connect with the infinite in a deeply personal way. That quiet moment when a parent points to the stars, naming constellations for a wide-eyed child, is a thread in a tapestry older than history. It is a story passed down not through genes, but through shared wonder, connecting generations under the same infinite sky. These personal encounters with cosmic awe are not reserved for astronauts or astronomers. They are woven into the fabric of our everyday lives. One person described lying on a blanket during the Perseid meteor shower, watching silent streaks of light scratch the darkness. In that hour, the frantic noise of daily life fell away, replaced by a deep, humbling peace. It was not just watching a celestial event, it was feeling like a part of it, a tiny witness to a grand and beautiful display. Another found the same feeling not outside, but in the pages of a book about the Voyager probes, reading about those golden records, carrying greetings from Earth into the void, filled them with a poignant sense of our tiny, brave place in the cosmos. It was a lonely feeling, they said, but also a unifying one, imagining our entire world represented on that single, fragile artifact. These stories share a common thread, a sudden shift in perspective that makes personal worries feel smaller and our connection to something vast feel immensely larger. This is a feeling we can actively cultivate. Simple practices like spending just 10 minutes in true darkness away from city lights can recalibrate your sense of scale. Or try mindfulness under the moon, simply observing its craters and seas without any goal, allowing the sheer distance of that reflected light to sink in. When was the last time the universe truly stopped you in your tracks? Perhaps it was the unexpected clarity of Venus hanging in the twilight, or the humbling realization that the atoms in your hand were forged in a star that died before the Earth was born. These moments remind us that awe is a natural human resource, as accessible as looking up. This shared capacity for wonder is our common ground. It is what binds a scientist at a telescope to a parent in a backyard, both gazing at the same celestial mysteries. As we stand at the threshold of becoming an interplanetary species, this emotional connection to the cosmos may be our most vital guide. It fosters not just curiosity, but a profound sense of responsibility for our pale blue dot and any future worlds we may one day call home. Mars is no longer a distant red dot, but a future destination with real blueprints. The ambition to become a multi-planetary species is now a central project for companies like SpaceX, whose colossal Starship vehicle is designed as the first true interplanetary transport. This reusable rocket, standing taller than the Statue of Liberty, represents a fundamental shift from exploration to settlement, aiming to carry massive cargo and eventually hundreds of passengers on months-long journeys to the Martian surface. Elon Musk frames this not as a choice, but as a necessity for the long-term survival of human consciousness, arguing that a single planetary catastrophe could erase all our achievements. Yet the challenges of living on Mars are immense. The thin atmosphere offers little protection from cosmic radiation, and the barren, frozen soil must be transformed into fertile ground. Habitats would need to be pressurized and shielded, likely built underground or from local materials using 3D printers. Beyond the technology lies a deeper, psychological frontier. Imagine a community of pioneers living under a perpetually dim, pinkish sky, completely dependent on machines for air and water, separated from the rest of humanity by a minimum 6-month voyage and a communication delay of up to 40 minutes. The isolation and confinement could test the human spirit in ways we have only begun to study in Antarctic research stations. These are not just engineering problems, they are profound tests of our social and mental resilience. The Moon presents a closer, yet still formidable, stepping stone. Lunar bases could serve as proving grounds for closed-loop life support systems, where every drop of water and every breath of air is meticulously recycled. Here, we would learn to truly live off the land, perhaps by extracting water ice from permanently shadowed craters at the poles. But why stop within our own solar system? The dream of reaching another star requires thinking on a scale that dwarfs Martian ambitions. Generational ships are a theoretical solution, self-contained worlds that would travel for centuries. Multiple generations would be born, live, and die during the voyage, their ship sustaining a fully functioning ecosystem and a stable society with no memory of Earth. The ethical questions are staggering. What right do we have to commit unborn generations to such a journey? How do we preserve knowledge and purpose over hundreds of years of isolation? Carl Sagan offered a different, more philosophical perspective on our expansion into space. He saw it not merely as a lifeboat, but as a way to deepen our connection to Earth. He believed that venturing to other worlds would provide a new, clarifying perspective on our fragile home, underscoring our common humanity and the preciousness of the biosphere we must protect. This forward-looking perspective turns our cosmic awe into a tangible driver for global cooperation and technological innovation. It forces us to confront who we are and what we wish to become. Will our future among the stars be defined by the same divisions that have marked our history on Earth, or will the sheer scale of the endeavor inspire a new chapter of unity? The choices we make today will echo for millennia, shaping the ultimate tale of humanity in the infinite cosmos. Our cosmic journey is accelerating toward tangible new horizons, with missions set to launch within the next decade that will fundamentally reshape our view of the universe. In Chile, the Vera Sea, Rubin Observatory will begin its legacy survey of space and time in late 2025, scanning the entire southern sky every few nights with a camera the size of a small car. This relentless observation will create an unprecedented motion picture of the cosmos, discovering millions of new asteroids and mapping the mysterious influence of dark matter in greater detail than ever before. By the mid-2030s, the Laser Interferometer Space Antenna, or LISA, will open an entirely new sense. This space-based gravitational wave observatory, consisting of 3 spacecraft flying in a perfect triangle millions of kilometers apart, will detect the low-frequency ripples from events impossible to see from Earth, like the merging of supermassive black holes at the hearts of ancient galaxies. We will move from hearing the universe's occasional crashes to listening to its constant, humming symphony. The propulsion systems carrying these new eyes and ears are also evolving. Advanced ion thrusters, which use electric fields to accelerate charged particles to incredible speeds, are enabling spacecraft to travel farther and faster on less fuel. Imagine a spacecraft that can glide continuously for years, building up speed like a sailboat catching a steady wind, making journeys to the outer solar system and beyond more efficient and attainable. At the same time, new instrumentation is giving us sharper vision. Next-generation spectrographs attached to giant telescopes like the Extremely Large Telescope will dissect the light from exoplanet atmospheres with such precision we could identify potential biosignatures, the chemical fingerprints of life, on worlds orbiting distant stars. This surge in capability is being dramatically amplified by the entry of private companies. By developing reusable rockets and standardized satellite platforms, they are driving down the cost of reaching orbit, turning what was once a prohibitively expensive government-led endeavor into a vibrant, accessible marketplace. This commercialization is not just about launching satellites. It is about building the infrastructure for a sustained human presence in space, from private space stations to potential lunar logistics networks. The collective power of these public and private efforts promises a flood of discovery, ensuring that our repository of cosmic tales is about to expand in ways we can barely anticipate. Each new datum will not only answer old questions, but will undoubtedly pose profound new ones about our place in this ever more revealed and mysterious universe. These cosmic discoveries force a confrontation with the most fundamental questions of our own existence. If the universe is billions of years old and contains trillions of galaxies, what possible significance can one brief human life hold? This is the stark challenge of existentialism, a philosophy that finds profound freedom in this very absence of predefined cosmic purpose. Friedrich Nietzsche captured this terrifying liberty when he declared that God is dead, meaning we can no longer rely on an external, celestial script for our values. We are thrown back upon ourselves, forced to create meaning in a universe that offers none. The sheer scale of the cosmos seems to argue for a cold indifference to our hopes and struggles. Yet, this perspective is not a sentence to despair, but an invitation to maturity. The writer Albert Camus argued that we must imagine Sisyphus happy, the mythical king condemned to eternally roll a boulder up a hill only for it to roll back down. Camus suggested that even within this futile, meaningless task, Sisyphus could find purpose and happiness in the struggle itself, in his own defiant spirit. Our cosmic situation is similar. We are temporary assemblages of stardust on a tiny rock, aware of our inevitable end and our apparent insignificance. And yet we choose to love, to create art, to seek knowledge, to roll our boulder with dignity. This act of creating our own meaning in the face of a silent universe is the essence of a truly authentic life. This realization also reshapes our understanding of free will. In a cosmos governed by physical laws from the quantum to the galactic, where does human choice fit? Are our decisions merely the predetermined outcomes of a causal chain that began with the Big Bang? Or does the inherent uncertainty of the quantum world, where probability reigns, open a tiny crack for genuine agency? While science may never fully resolve this puzzle, the experience of choice feels undeniably real. Our ability to look upon the cosmos and question our place within it is itself a testament to a form of freedom, a capacity to transcend our immediate biological programming and contemplate the infinite. This cosmic perspective, born from awe, naturally expands our ethical circle. When we internalize the fact that every human being is made from the same rare star stuff, living on the same fragile world adrift in a vast emptiness, our ancient tribal divisions begin to seem not just petty but cosmically absurd. The philosopher Peter Singer argues for an expanding moral circle based on the capacity for suffering, a concept that feels all the more urgent when seen from the vantage point of space. Our planet is not a collection of separate nations, but a single, living system, a pale blue dot that is the only home we have ever known. To feel awe at the universe is to feel a deeper responsibility for the only other conscious beings we know, and for the biosphere that sustains us all. We see this profound connection expressed not only in philosophy, but in the poetry that gives voice to our wonder. The poet Mary Oliver, looking up at the night sky, asked, "Tell me, what is it you plan to do with your one wild and precious life?" Her question lands with greater force against the backdrop of an infinite cosmos. Our time is brief, our world is small, and our existence is a statistical miracle. This knowledge does not trivialize our lives, it charges them with a new and urgent significance. The cosmos, in all its terrifying grandeur, becomes a mirror, reflecting back the choice we must each make to fill our fleeting moment with purpose, compassion, and a defiant, beautiful love. Walt Whitman did not just look at the stars, he felt a kinship with them. In his poem, When I Heard the Learned Astronomer, he describes walking out of a lecture hall filled with charts and diagrams to look up in perfect silence at the night sky. His words capture a truth science alone cannot express, that the visceral, mystical encounter with the cosmos transcends any academic proof. This is the domain of poetry and literature, where the ineffable feeling of cosmic awe finds its voice. Maya Angelou, in her poem When I Come to You, speaks of arriving with the dust of stars on her feet, a simple, powerful image that roots our very bodies in a celestial ancestry. For centuries, writers have used the vastness of the universe as a mirror for the human soul. Dante's Divine Comedy is a cosmic roadmap of the medieval imagination, journeying through the concentric spheres of heaven, each one bringing him closer to a divine light he admits his own words fail to capture. He uses the metaphor of the cosmos to explore the geography of sin, virtue, and redemption, mapping the internal human struggle onto an infinite external canvas. Modern novels continue this tradition. The silent, star-filled void in science fiction is often a backdrop for confronting isolation, while the sheer age of the universe in works of realism can make a single human lifespan feel both tragically brief and poignantly precious. The primary tool in this literary arsenal is metaphor. How do you describe the indescribable? You compare it to something knowable. A galaxy becomes a swarm of fireflies. The expanding universe is an inflating balloon. Dark matter is the unseen wind rustling the trees. These are not just pretty phrases, they are cognitive bridges, allowing our minds to cross into territories that pure data cannot reach. They provide an emotional vocabulary for an experience that can otherwise leave us speechless. One contemporary poet admitted the daunting challenge, noting that to write about the universe is to constantly fail, because language is finite and the subject is infinite. Yet we keep trying because the attempt itself is a form of reverence. This artistic expression does not compete with scientific explanation, it complements it. Science tells us how the heavens go, poetry tells us how to go to the heavens. They are two different languages describing the same profound reality, two distinct paths up the same mountain. This beautiful intertwining of disciplines, where the artist's intuition meets the scientist's rigor, reflects a fundamental human drive to understand, a quest that extends from the poet's pen to the classroom, shaping how we learn to see our place in the grand whole. A child's first gasp at the ringed majesty of Saturn through a telescope eyepiece is a quiet spark that can ignite a lifetime of discovery. This transformative power of direct experience is at the heart of modern science education, where innovative programs are moving far beyond textbooks to cultivate cosmic curiosity. In classrooms and community centers, students are no longer just learning about the solar system, they are building it. They manipulate digital simulations to slingshot a virtual spacecraft around Jupiter, feeling the complex dance of orbital mechanics in a way a diagram could never convey. They use simple pendulums and prisms to uncover the same physical laws that govern distant pulsars, connecting their desktop experiments to the grand workings of the cosmos. These hands-on activities are gateways, transforming abstract concepts into tangible, personal understanding. The immersive world of the planetarium offers another profound portal. Under a domed sky, the abstract scale of a light year becomes a visceral journey, flying through the pillars of creation or watching a supernova unfold in slow, magnificent motion. One educator noted that after such a show, students do not just have more answers, they have better questions. They ask why the universe is expanding, or what it would be like to stand on a planet with two suns. That shift from what to why is the birth of critical thinking. This mission of inspiration is championed by organizations like NASA, whose STEM initiatives provide curriculum resources, host student challenges to design Mars rovers, and connect classrooms directly with astronauts on the International Space Station. University outreach programs bring graduate students into elementary schools, demystifying who a scientist is and showing that curiosity is a universal trait, not a specialized credential. The underlying goal is not to create a generation of exclusively astronomers, but of informed citizens equipped with the tools of inquiry, skepticism, and wonder. These skills are the bedrock of a thriving society, enabling young minds to navigate a complex world, to distinguish evidence from conjecture, and to approach problems with creativity and resilience. The question then becomes, how do we, as a community, nurture these sparks? Supporting local science education can be as simple as volunteering at a school's star party, donating to a library's telescope lending program, or advocating for robust funding for science in our schools. By investing in these opportunities, we do more than teach facts, we pass on a legacy. We ensure the timeless tales of the infinite, from the birth of stars to the nature of dark matter, will find eager new minds to interpret them, guaranteeing that our collective journey of cosmic wonder will never end. A spiral galaxy and a swirling hurricane share an eerie, beautiful resemblance. This is not a coincidence, but a clue to a deep truth about our universe. Patterns repeat themselves across scales, from the microscopic to the cosmic, in a phenomenon known as scale invariance. The branching veins in a leaf mirror the tributaries of a great river delta, and both look strikingly similar to the forked lightning bolt that splits the sky. These recurring shapes hint at a universal language of structure and flow. Perhaps the most mind-bending comparison lies between the human brain and the cosmos itself. A single neuron, with its sprawling network of dendrites and axons, bears an uncanny visual resemblance to the vast cosmic web of galaxies, with its great filaments of dark matter connecting brilliant galactic nodes. One is a map of thought, the other a map of the universe. Both are networks of information and energy, organized by the same fundamental principles of physics. This interconnectedness is the heart of systems theory, which teaches us that the universe is not a collection of separate objects, but a single, dynamic web of relationships. Every atom in your body was forged in the heart of a long-dead star, and the energy that animates you once powered the birth of a galaxy. The carbon cycle that sustains life on Earth is a local expression of the great cosmic cycle of stellar death and rebirth. We are not just placed in the universe, we are woven from its very fabric. The poet and farmer Wendell Berry understood this deeply when he wrote that the Earth is what we all have in common. Every particle of your being is in constant, silent conversation with the whole of existence. This holistic view transforms our sense of awe. The cosmos is not just an immense void we look upon from the outside. It is a single, breathing entity, and we are a conscious part of its unfolding story. Our journey of wonder, which began with a gaze at the stars, brings us full circle to a humbling and empowering realization. We are the universe becoming aware of itself. Our journey through the cosmos has been a tale of profound emotions and even deeper mysteries. We began with that humbling feeling of awe, the breathtaking sense of being a tiny part of something infinite. This single emotion propelled us to explore the universe's fiery birth in the Big Bang, to grapple with the invisible architecture of dark matter and the strange anti-gravity of dark energy. We ventured to the edge of reality at a black hole's event horizon and pondered the possibility of an infinite multiverse beyond our own. At every turn, we found that the universe speaks a language we are only beginning to learn, a dialect written in the mathematics of relativity, the uncertainty of the quantum realm, and the silent, patient rotation of galaxies. This cosmic conversation is not for scientists alone. It has always been a human dialogue expressed through the equations of Newton, the brushstrokes of Van Gogh, the poetry of Whitman, and the myths of every culture that ever looked to the stars. We engage with the infinite not merely to collect facts, but to find meaning, to understand our own brief, brilliant moment in the grand sweep of cosmic time. The universe does not ask for our worship, only our curiosity. It invites us to continuously question, to wonder, and to remain forever students of its vast and beautiful complexity. As the astrophysicist Neil deGrasse Tyson so eloquently reminds us, we are not simply living in this universe. The universe is within us. The very atoms that form our bodies were forged in the hearts of distant stars. We are star stuff, and in our longing to comprehend the cosmos is, in a very real sense, comprehending itself. So the next time you find yourself beneath a clear night sky, take a moment to simply look up. Let the light from stars that died long ago fill you with that ancient, transformative awe. See the constellations not just as patterns but as stories. Feel the connection to everyone who has ever wondered at that same expanse. We would love to hear your own stories of cosmic wonder in the comments below. Where were you when the universe made you feel both infinitely small and deeply connected? If these journeys into the mysteries of space have sparked your curiosity, be sure to subscribe for our next exploration. The greatest discoveries are still ahead, waiting for us to peer just a little deeper into the infinite.